What I'd like to do is start up with two problems out of the textbook in section 2.6. This deals with continuous functions. One of the problems, the first one, will be solely what I call busy work problem. It's to really find out if you know what continuity is all about. Second problem is a little bit more practical, although you might not notice it from the way it's phrased in the book. And it's also a good lead-in to the next chapter on derivatives, why we'd want to look at tangents to curves in the first place. Now the first problem, let's take number 35 on page 85. Well, to begin with, it looks complicated because it's one of those multi-line definitions. Okay, there's your function. And if you'll recall, last time we had problems of the following type. The easy one was, here's a function, is it continuous at this point? Yes or no. That's about all there was to that. Second problem was, here's a function, you tell me where it's continuous. Find all points of continuity, or discontinuity equivalently. That's a bit tougher. This problem falls into a third category, which is basically make this function smooth, or continuous as we call them. So you're not just handed something and you're supposed to analyze it, but you are supposed to adjust it properly in order to make the thing smooth. Emphasis is on you make the function smooth. Quick item of reference, I talked last time about removable discontinuity. That was a function that perhaps had a gap in it at one point, and by properly filling the gap, you make it continuous. That's a relatively easy problem to do, assuming that you have knowledge of what the function looks like to the left and right of that point. This one's a little bit more difficult, but if you really stop and take it slowly, you'll find that they're not as bad as they first appear. Especially if you at least consider what it means geometrically. And then when we get into the algebra, which is easy, you'll find why the solution does what it does, I think. Let's start out with a little bit of a picture of what's going on here. We've done this kind of a problem at least up to the statement of it and maybe making a graph of it. This function is one thing to the left of 2, so let's put that down as our dividing point. Over here to the left it's one item, namely cx squared minus 3. To the right it's got another identity altogether, cx plus 2. Now, question? It's supposed to be greater than 2, greater than 2. Right, thank you. Right. These should be the same points. If not, we don't even have the thing defined, or it's doubly defined, which is no good either. So let me take our first or left-hand side here and graph that in red, or at least one of the possibilities. Now, the problem is to make this function continuous. I didn't continue on and say by choosing appropriate value or values of c. But to show you what that c is all about, let me show you that this function right here is some kind of, well, do you know what that shape would be? Cx squared minus 3. What if c were equal to 1? Let's just make it easy. X squared minus 3. It's a parabola, and it intersects the y-axis at minus 3. Now that's still a parabola, but it may have a different shape than when c equals 1 or c equals 2 or 5 or whatever. In fact, if it were negative, the parabola could open downward, but let's just pick this picture right here as our representative for some value of c. Now that's good up to and including 2. Okay? That's as far as we go with that function. Next, we have to pick up the identity for f past 2, and that's this function, cx plus 2, which is, what do you think? Straight line. It's a straight line that always passes through 2, and in fact, c happens to be its slope. So let me pick a 2 here and draw an example of that function. So this will be cx plus 2 for some c, and this thing over here is cx squared minus 3 for some c as well. I'm not claiming they're the same c's. I'm kind of independently looking at the two pictures simultaneously. well, I got carried away here. I shouldn't have put this part in. If I'm attempting to draw just the function f, the blue line only extends to the right of x equals 2. Okay, I should have chopped off the left-hand part because that's not a part of f's definition. So here's your function f. It comes in like a parabola into 2 from the left and leaves like a straight line from the right. Now, to make the thing continuous, obviously what do we have to do? In so many words, make them meet. Exactly. How are we going to pick c so that these two items meet? That's all we have to do. Now, they may meet at a funny shaped corner. You know, I'm suspicious that maybe it'll look like that. That's not a problem. That's a continuous function in that sense that you can draw it without raising the chalk off the blackboard. So that's okay, for now anyway. What do you do to make them meet?
You have to change the slope.
Well, yes, geometrically, this line over here is going to have to be changed, and this curve here has to be either made more concave or less concave, something like that. That's great intuition, but here's where we got to switch to algebra, at least as far as I'm concerned. The thing to do is to switch to an algebraic statement that makes sure those 2 points will meet, the blue line and the red line. Now, what would it mean to algebraically have the two meet?
To have the same f value or evaluated function at 2.
Exactly. As Mr. Bond just said, at x equals 2, both the red dot and the blue open circle are going to have to meet. They have to have the same f values. So what that means is the straight line at 2, here we are, here's c times 2 plus 2, we're going to force that to have the same value as the red curve also at 2. That's going to have altitude 4c minus 3. Okay, if those two are equal, then at the same x-coordinate, both curves have the same y-coordinate, and they would match then. And then you can see it's a very trivial algebraic problem at this point. In fact, the geometry, seeing what's going on, is the most significant part of the problem. Because over here, what do you have? 4c minus 3 is 2c plus 2. I hope all of you can do this kind of a problem. C, in fact, there's only one value that works, c equals 5/2. And that would make a match. That's all there is to it. But of course, this is a problem that makes you think about it a bit. What is continuity? And once you establish what it is, perhaps the algebra could be tough. If it were a cubic and a parabola, you might have a cubic equation to solve, and that might be rather difficult.
I was going to say, suppose could you have like two different values that c can equal?
The question is, could you have two different values? By all means. I think the next problem in the book has a c squared in it somewhere, which allows you to come up with a couple of values where they match. So the answer is yes, it could happen. And I think it does happen in the next problem. Okay. Well, you've got one like that, I think. We'll see how you do on it. The other problem I wanted to entertain you with today is number 54, same page. Now that's quite a mouthful to say all that, but basically you're supposed to show a certain polynomial has a root, or I should maybe say a solution to this equation that lies between 0 and 1. Well, this problem we did over here is almost a good lead-in because although it was trivial, this is a first degree equation that we have to solve. We could write it as 2c minus 5, or let's make it x's. 2x minus 5 equals 0. That was easy, but as I just told you, you might have a c squared here, which would make it quadratic. And that's pretty easy because you probably could factor it, or if nothing else, you could put the quadratic rule down. Solve that by quadratic rule. It's one you can just punch in and get the results for. You're all supposed to be familiar with that too. Turns out you could also solve the general cubic equation. Ax cubed plus bx squared plus cx plus d equals 0. There are formulas for that. I would bet any amount of money that no one in here knows it, because I don't know it either. You can find them in books. You can probably solve a fourth degree equation, but there is I think a statement in mathematical literature that says there is no one formula which will allow you to solve any fifth degree equation. You see, the quadratic equation always works. You might get imaginary roots, but you get the roots. Over here, there's no formula that gives you all roots for a general fifth degree equation. So this is not a badly posed problem. They do come up in mathematics here, but also out there in the scientific world, there are just lots and lots of situations where you're working there, your boss comes up and says, hey, we need a solution to this so we can get the satellite off the ground for some reason. Find it. Find the root for this equation. And you remember that in this course, the teacher said there is no general formula for such a thing. So what are you going to do? Well, the first step is, let's see if there is one, because, you know, as an example, you might have some parabola that doesn't even cross the x-axis. And so, in fact, there is no root. There is no, for this particular quadratic expression, there is no root or intersection with the x-axis. And that might be the case here. Your boss is asking you for a root, but it turns out there are none. Or you ought to establish that there are none, or in fact there is one. Just about where is it? Well, the story that you would give your boss up to a point would be something like this. Here's the interval of interest. And you might say, well, gee, what we're talking about is a polynomial, p of x, and we're interested in whether or not, or where, p of x is 0. That is, where does the curve related to the graph of p of x cross the x-axis? Or does it cross the x-axis? Well, your problem leads you along and says, show that it does. And the way to do that is as follows. What's p at 0? Well, that's easy. 1. Just put 0 in for x. How about at the right-hand endpoint? P of 1 is 1 minus 3, that's minus 2, minus 2 more, that's minus 4, minus 5, minus 4, I believe. You can check my arithmetic, but I'm pretty sure it's negative. And the reason I'm interested in that is that says here is p at 0, here is p at 4, and what's true about polynomials, among other things? They're continuous, they're smooth. It means there are no gaps, no jumps, no bad wiggles. And what that says to me is this polynomial, to get from here down to here without me raising the chalk off the blackboard, somewhere, at least once, has to cross the x-axis. So the proof that such a root exists is what your book would phrase more generally as the intermediate value theorem. If a function has value 1 at one point and minus 4 at another, then it has to pass through 0 at least once. Now, this being a fifth degree equation, it might pass through 3 times. That's a possibility. I'm not ruling that out. But at least once is there such a root. That doesn't really help you with your boss. You've shown him that it does exist. He's going to then emphatically say, where does it exist? That's a little bit out of the realm of our math, but I want to show you perhaps why one looks at tangent lines to curves. And a trick we'll come up with in a few weeks would go something like this. As an example, you maybe look at the graph on a CRT or Tektronix CRT in the yard. You look at it and say, gee, it looks like it's roughly between 1/4 and 1/2 maybe. So what you would do is say to the machine, start at some point like 1/4 or nearby, and take the tangent to the curve and find out where it crosses the x-axis. Now notice the difference. very complicated curve, we don't know where it crosses the x-axis, but as we will see, it's easy to come up with tangent lines. We've done it a few times already. And it's easy to find out where tangent lines, or any line for that matter, crosses an axis. So that blue line is easy to come up with. What good is it? Well, we can start all over again and say, let's do the whole process once more, drop down to the curve, and take another tangent line, and come back to the x-axis. And you can see what's happening. We are, in a sense, honing in on that root. And so after 3 or 4 tangent lines, you're very close to the root. As close as you wish, the more tangent lines you take. Well, your response would be, that sounds like an awful lot of work. But remember, we're working with lines. This has a very simple equation. If you start at this point on the curve, it's very simple to establish where the straight line, the tangent line, crosses the x-axis. And so it's just a matter of applying that rule once, twice, 4 times, 5 times. And what way would you apply such a rule, such a numerical rule? On your calculator? Maybe, but more likely on a computer. And what you do is you write a big loop which says keep on going until the answers that you get, in other words, where these blue lines cross the axis, start looking pretty much the same. Because where they start looking the same probably is where this red curve crosses the axis. I've gone down the story much too far. This is what we're going to call Newton's method in several weeks. But it's one way to introduce you to one application of why, given a curve, one would want to establish what the tangent to the curve is at any particular point. Okay, so to get us into the next chapter, let me take as a problem something that's somewhat familiar to you. I think we had a quiz problem along these lines. And we've actually had a couple of problems like this before. The main idea, of course, is to find the slope of a curve, which is the slope of a tangent line to the curve. The difference in this problem is that we're to find it at any number a, not a specific number like 2, but any value whatsoever. By way of reference over here on the right, this is essentially the same problem, more complicated because it's a higher degree, but that's roughly all you need. Given a point on the curve, if I knew what the slope is, then I could readily find out where that thing intersects the x-axis, and that's the whole key to that Newton's method. Okay, let's see how this goes. It goes just like we've done it, I don't know how many times before. First, I would suggest you try to draw something like a graph of the function. And if it's not obvious what the graph is, you ought to plug in a few points and see what's going on. Let's do that just to get a feel for the shape. Let's do some of the traditional values. And let's see, if you had a -1 for x, you get 6. With a 0, you get 2. With 1, you get 4. And with 2, you get 12. Okay? No complaints out there. So I've got 4 points, and let me try to plot them. Let's call this 6 up here, 2 here, 4 here, and 12's way up here now. Okay, so maybe that's the shape, and no surprise, it is parabolic because it's a second degree polynomial that we're looking at. Now here's basically the problem. We're going to start at any a value for x, go up to the curve, and somehow establish what the slope of this tangent line is. It's an old story. We've done it before. What we did, we'll do it again I guess, is to take another point on the curve, let's call them P and Q now, find the secant line through those 2 points, and I mean literally find because we do have 2 points to work with, then fix the point P, let Q slide along the curve to P, let the red line rotate into the orange position, and let the red slope become the orange slope, which is what we're after. Now what makes this problem somewhat different is that the evaluation for the secant slope is somewhat tougher in the sense that it's more abstract. Before we had some real numbers here that you get your hands on, but right now it's rather notational. To make life pleasant in a sense that it's going to look like what you see in the book, what you'll see is that for the point Q, let's establish that that has an x-coordinate which is h units away from A. So the x-coordinate for Q will be itself A plus h. There's no real good reason to do that other than it makes some of the algebra later on somewhat simpler. Well, that helps us now because we can look at this triangle we've dealt with before and say, in going from P to Q, we are talking about a run along the x-axis of h units. And if that's the case, what's the rise going to be, the corresponding rise? Okay, well, the rise would be this distance right here, which is the y coordinate for P. That would be f of A. Just to keep things simple, let's call it f of A. Take that away from the y coordinate for Q, which would be f of A plus h, because Q is sitting right over the x coordinate A plus h. So the rise then would be that difference, f of A plus h minus f of A. And then we're ready to pretty much go to town algebraically. The slope we're after, the tangent slope, m, as before, is the secant slope limit as the variable point approaches our fixed point P. And by what we've just written down, that's equivalent to letting h, the distance between the points, go to 0 of the rise over the run that we've just established. For those who have carefully studied your homework, this looks awfully familiar in lots of different places. In fact, your last quiz was to, in fact, simplify such a numerator, and I believe it's exactly the numerator we're working with today. So let's do that now. F at A plus h, well, you're supposed to take the argument and square it, multiply it by 3, it says, subtract the argument, and add 2 on. That's f of A plus h. Next, in the numerator, subtract f of A. That means just plug in A. That says take A, square it, multiply by 3, subtract A, add 2. So we've plugged in and gotten that second term in the numerator. The whole thing now is to be divided by h. Okay, again, here is f of A plus h. Of course, the other term is just f of A. The secret to making this problem, and like a lot of your limit problems work, is to get rid of the bad character. This will always be the case for derivatives. You'll have a 0 in the denominator. If you're going to do it by hand, you're going to have to eliminate that 0 somehow. Well, the trick is to simplify the numerator, which means to write it out, cancel as much as you can, and with any luck, h's will cancel throughout. Let's do that. I'm going to have to do this in not too much space, but I hope you can read it pretty well. If you square all this out, you're going to get 3a squared plus 2 times 3, or 6ah, plus 3h squared. That's out of the first term here. The second term would be a minus a minus h, third term plus 2. So that's what your f of a plus h expands into. Now let's take the negative sign and subtract off what's in f of a. That'd be a minus 3a squared plus a minus 2. I think in our quiz that was a big hang-up. People didn't get that negative sign distributed throughout. Now when you go in, you should be able to cancel anything that does not have an h in it. And that's a word of caution. If you end up with terms that don't have h's, I bet you've made a mistake. For example, that a there, I can look at it and say it's going to have to cancel somewhere. Sure enough, it does way over here. And the same is true for the 2. So what we're left with is limit as h goes to 0, 6ah plus 3h squared minus h, that's all that's left on top, I believe, and an h on the denominator. And sure enough, just as I suggested, there is an h in every one of those terms, which you could cancel now because h isn't 0. It's a 1, this will be an h, and this will be a 1. Our limit now, very simply, is limit as h goes to 0 of 6a plus 3h minus 1. And I hope at this point all of you can say that's a polynomial in h, so we just evaluate it at h equals 0. And what you get finally here is a 6a minus 1. And if you're like me, when you're all done, you wonder, not only did you do it right, but what did you just do? So you follow all this backwards. Ah, yes, the thing we were after, namely the slope of the tangent line over here, regardless of what a is, has slope. The slope is equal to 6a minus 1. And for one thing, it tells me that, gee, at the origin, I guess I did a pretty good job of drawing it, actually. That's because I drew it 2 periods ago in a previous section. When I drew it then, I actually had this thing come and bottom out at the origin. But when I get done, I know that couldn't be the case. At the origin, it has slope minus 1. It actually is going downhill, not at the origin, pardon me, but at the y-axis, it's going downhill with slope minus 1. The tangent line there has slope minus 1. And you could find out the slope anywhere, or, gee, even more introspectively, you could solve this and say the slope is 0 at a equals a sixth. That means a horizontal tangent, or the lowest point, is at 1/6. So you get a lot of information out of that so-called slope function. And what we're going to do is call it the derivative function next time, as well as say, I sure would like to avoid this if I could. And in saying that, what you're saying is I'd sure like to learn some rules for finding derivatives, and we'll spend a lot of time on that too. So read ahead, look at the pictures, look at some of the results, and we'll come back and discuss them here in class next time. Well, they're inside. Center in the. This one over here. Get that formula.